then if you move the electron to a higher level here, right? If the electron come back from this to one of the field state, or the electron come back to fill back this hole, right? Then you would have high energy. You have X-ray emission, right? But if this electron come back to fill a shallower energy level, you would have light emission or visible light or UV light emission. That's what they call it. They say light. It just means that photon with a longer wavelength. That's all they mean. Okay. So of course, why the light they draw so close to the surface? The reason is that X-ray, of course, can penetrate a lot more, can come from a lot more, can go through material a lot more. Whereas if you are talking about optical light, visible light, or ultraviolet light, they do not penetrate that much. So that means that they have to come from near surface in order to emit. The creation of this light, right? This light still exists. It still exists deep down. It's just that if you create this visible photon deep down in here, it won't get out because it gets absorbed. It gets reabsorbed by the material. So the reason really you see it is because you only see the surface region is because of absorption of the light. Okay, and same with your pole wall effect, right? Because as you go scatter down, your backscatter electron cross-section, so-called cross-section, which means probability of backscattering, will continue to decrease. It will continue to occur, but only the surface region will take place. Same with the OJ electron, because the OJ electron, as long as you have electron interacting with material, OJ decay will occur, even down deep here. But the OJ electron that emit here will not make it to the surface, and therefore you cannot see it. Okay? So bear that in mind. It's not just the physics does not occur deep here. It's just that the emitted particle cannot make it out from the surface. And that really is the one that gives you the surface sensitivity. And why is that? It's because of this plot, right? Remember, I talked about these two plots at great length. It's because this is the universal inelastic mean free path, because you really depends on the kinetic energy, how far the electron can make it to the surface, right? The escape depth, right, depends on how fast the electron is, right? And so it really is kinetic energy dependent, and doesn't matter how you create where that is. And in the case of OJ electron, they are down here, so it's very surface sensitive. Okay, so I think I think people should keep that in mind. It's a qualitative plot, but I thought more about it because I thought that people in material science are going to use a SEM eventually. They need to understand the physics, and this is qualitative physics that involve, and it will help you in terms of understanding the basic principle of how these things work, even though it does not involve mathematics, but it is crucial to appreciate the information content that you get. Okay, so we are a little bit behind in terms of our position in our material. We are maybe a lecture behind. So I'm going to move a little bit quicker now. So just to finish up, we have this microscopy, and then you have electron diffraction down here, which we'll talk but a little bit more later on when we talk about surface structure. But I'd like to give you a quick, brief idea what it is, so that when I talk about surface structure, people may remember what I said now. So we'll talk a little bit more later about surface structure. This is low energy electron scattering, or low energy electron diffraction, or simply electron diffraction. Is a popular technique. Almost every surface machine will have a device like this. It looks something like this. It's on a flange. If people haven't seen what a surface machine looks like, they can come to And usually, what you're detecting is that you have a electron beam of about 100 electron volt, and you look at diffraction pattern really. So usually you have a electron gun, you hit the sample, and because your sample consists of atomic position points, then you have scatter, you have diffraction pattern coming out. And we'll talk a little bit about the origin of these diffraction pattern when we go into surface structure shortly. So basically what you got is you have these concentric hemisphere that you have, and at the back you have a curved hemispheric screen, and you detect, essentially you detect spot look like this. If you look at the phosphorus screen at the back end, you would detect. So all this slow moving electron, and the last two grid, there's a grid, hemispheric grid, between the last one and the phosphorus screen, there's a high voltage, and the high voltage accelerate this slow moving electron to several kilovolts, several thousands of volts, and impinge on the phosphor, and you can see it visibly by your bare eye. So you see all this little spot. I don't know if you can, maybe you can barely see it on the screen, and that's what you see on this. And by looking at the relative position of this pattern, right, you can deduce the surface arrangement, and if you can control the kinetic energy of the electron beam and measure the intensity of one particular spot or the other particular, one or two particular spot, you can actually determine where surface parameters structure itself, like A and B spacing, this sort of thing. And we'll talk a little bit more about it. I just want to give you a quick tour of what we may use in terms of doing that. And the key point is using what we learned in quantum physics is that all material has a wavelength. It's known as the Pauli wavelength. This is known as matter wave, so we don't think of the electron just like a particle. We think of them as wave as well, and if you look at wave nature of the electron, it is at 100 electron volt is about of the order of 1 angstrom wavelength. And this is very nice because 1 angstrom is the typical crystal spacing of your lattice, and this is why you would have diffraction phenomena. Okay, so when your wave is very close to your grid, which is your surface, then you would have diffraction, and you would have these spot diffraction patterns. Okay, and this is why you have X-ray diffraction as well, because X-ray diffraction, you choose your X-ray source. Usually, copper X-ray source is about 1.5 angstrom, and that's perfect for looking at material. You would have diffraction phenomena from these. Okay, you would have other more advanced technique like surface extended X-ray absorption fine structure. I don't want to go too deeply now into this one, but just to mention that you could do more advanced thing, and the way this works is that it's also a diffraction-based technique. And what you do is you send in an X-ray beam. Instead of measuring diffraction pattern, you measure what happened to the profile, to the absorption of this X-ray profile. So you send in, it's very much like your UV absorption spectrometer that we use in undergraduate lab. You send in a photon, you measure the photon intensity come out that go through. So X-ray absorption is actually like this. Instead of you sending a UV photon, you send in X-ray, right? And then you measure what come out. So really, it's like you have material here. Your X-ray come in like this, and you measure X-ray come out. Okay, and you have I naught and I pi like this. So you measure absorption. So you remember I pi divided by I naught is absorption, or related to your cross section that people using Beer's law. We'll come back to talk a little bit about it. It's a rather simple technique, but if you measure I, this